Swayam Prabha. Digital India. Educated India.
Okay, so in the last class we are trying to figure out for turbulent flows the various scales those are invoked, and to understand that we wrote down the Navier-Stokes equation in terms of the vorticity. So, this is the equation that you would have. I did say it today, again I emphasize that in writing that vorticity transport equation you get a better picture of the various processes those are involved. For example, this is your substantive derivative on this side, but this is the additional term which we call as the vortex stretching term is important, because this is only present for 3-dimensional flow and not for 2-dimensional flow. So, this point of view actually helps you in understanding, distinguishing between 2D and 3D flow field. And also this is a nonlinear term. So, we would like to see how this nonlinear term affects the flow dynamics. So, if we then consider again for the purpose of analysis the flow to be inviscid and not have any body force, or even if it is there, let us say this is given as a conservative force, then the body force does not come into the vorticity transport equation, right. And then what happens is we get the simplified equation like this. So, the derivative rate of change of vorticity is solely driven by the vortex stretching, right. So, this is the term that we discussed. Let us say what happens is that this is only present in 3D flows. In 2D flows, omega and the grad operator are in quadrature. So, they would not have any problem, and I was explaining this yesterday by considering a special case where let us say we identify a fluid element of this cylindrical topology with the vorticity predominantly in the let us say in the z direction, and if we look at the velocity of the two ends given by u top and u bottom. So, if it is kind of stretched, then what is the consequence that we wanted to figure out. The way we have drawn the velocity vectors here, it shows it is kind of a stretching term, and then once you see that what happens is that the fluid element is going to be stretched, and we are talking about inviscid flow. So, our all kinds of momentum are conserved, including the angular momentum. Angular momentum is now given by I z z times omega z, right. So, basically if we are looking at the angular momentum here as simply I z z into omega z. Now, what happens is because of this fluid element stretching due to this rate here del u del z, what will happen is if this is greater than 0, then what will happen, the element stretches and I z z decreases. As a consequence, what you are going to get is that omega z is going to increase. So, this is the consequence of that vortex stretching term, because that is what it is doing, because to maintain the angular momentum conserved, if I z z come down, this must go up. However, if you look at globally over the flow field, the overall angular momentum should be conserved also, and the vorticity also would be conserved. And then what happens is, if locally there is a variation in omega z, there must be a corresponding reduction in other components, right. So, that comes out what we can show in terms of a tree diagram, like if I have omega z here, and then because of this stretching term that omega z is increasing, but then that will affect omega x and omega y. So, we get a corresponding variation in omega x and omega y. And again, if the fluid element experiences some kind of a stretching, let us talk about stretching. Compression also will bring in exactly the same effect, but it will be just opposite in sign. Vorticity will be a changing sign, but if you look at the corresponding contribution to entropy, it will always be additive, right. So, entropy keeps changing. So, if I now have these elements omega x and omega I change, that can furthermore bring change in omega z and omega y, and the same way this will bring in change in omega x and omega z. Then furthermore, if we go one generation down, this omega z will affect omega x and omega y. This will bring in change in omega x and omega z. So, this is a kind of a composite picture that you can keep thinking about that is going to happen. And if you keep on doing it further down, then what you are going to see is that although you started off with, let us say, an inhomogeneous change in omega z, subsequent change is going to be sort of all pervading, because you are going to see changes happening in omega x in 3 times, omega y 3 times, omega z 2 times, and if you look at the next generation, each one will spawn another couple of them in quadrature. So, what happens is this keeps on happening going down the tree. You are going to see this smaller and smaller changes, but they are going to be isotropic, right. So, this isotropic behavior of vortex stretching also is used in turbulence modeling when one does large eddy simulation. There, if you are looking at the vorticity at the smaller scales, they are going to be as isotropic as it is indicated here. And if this is not resolved in your computation, then you can model it, because now you are armed with that additional information that this is isotropic. See, basically modeling is always helped once you know what is happening. For example, previously we saw in case of time averaged equation how Reynolds stress was correlated with the mean strain rate, and that helped us develop turbulence model. So, in LS model also we make use of the fact of that at the small scale, at the subgrid scale, we have isotropy. That is a very hopeful sign and good news for one to do that. Well, in this following we just simply said, look, you do not really need to only talk about entropy or anything, but you can look at the nth moment of the vorticity and find out its time rate of change, and then you are going to get this, right. This we can put it inside. So, we will get n omega raised to the power n minus 1 times del omega del t. Now, from the vorticity transport equation for inviscid flow, this is what we have. This local change is given by the convective change as well as this vortex stretching. So, we can put it up there, and that is what we did in yesterday's class. And what we really found was that we get 2 sets of terms. One comes out from the convective term, another comes from the stretching term. The convective term can be written down in terms of this as a volume integral, and this is the stretching term that is written like this. This could be, because this is written in a conservative form, it is a divergence of omega n u. So, we can convert it into a area integral over the control surface, and this is what we get. Now, of course, for 2D flow this does not exist. So, we know that the first term is 0 if we consider the boundary condition. So, what happens if you are looking at the far field boundary, the vorticity itself is 0. If you are looking at the solid boundary, no slip condition will ensure u is 0. So, this will not be 0, this is already absent. So, for 2D flows you find that any order moment that you look at for vorticity does not change with time, right. That was what we were talking about. Remember that if omega z increases, then correspondingly omega y omega, that comes about from if I look at some kind of a norm, say entropy, right, that will be omega x square plus omega y square plus omega z square. So, if omega z square increases, it better be that omega x and omega y should decrease, and that was this whole idea of this tree diagram that we had. So, this is the one thing that we can establish for 2D flows. For 3D flows you can very clearly see the time rate of change is given by this, the stretching term. So, stretching is a very important role to play for 3-dimensional flow. It can tell you how the various moments of this vorticity can change with time. If you add the viscous effects, of course, this term will have to come in. This will also affect the moment here with respect to time. However, when we talk about viscous flow, we need to also understand that the solid body itself is a source of vorticity generation, right, because of the no slip condition vorticity will have to be generated. So, that adds to the moment, right. So, whatever we are discussing strictly for inviscid flow, for viscous flow they are all altogether different. So, we need to keep that in mind. So, let us try to understand what we get by defining what we call as the entropy here. Is the square of the vorticity, and this is the generic definition in terms of the permutation symbol E I J K and E J M, and this is what we discussed, that if they are in order, in cyclic order, then that is positive 1, but if the cyclic order is broken, it becomes some anticyclic permutation, then it gets a -1, and if any of these two indices are same, they actually do not contribute anything. So, what happens is this entropy can be then written down as a combination of two sets of terms, which we have written it down here in terms of this Kronecker deltas, and you can see that these will only work when your m will become equal to j and k will become equal to n. So, that gives you the first component, and this is the other component when j becomes equal to n. Means this is u j, and when k becomes equal to n. So, that will be this. So, that is what we are getting. So, this is basically a set of two sets of terms. This is nothing but the gradient u square. So, what you find that entropy is related to the gradient of the velocity field, that norm. This term that comes about from the second set is going to be 0 if you are talking about a periodic problem, or if you are talking about no slip boundary condition incorporated there, will make that second term equal to 0. So, in a sense what we are saying that for general case, the entropy measure is given by the velocity gradient measure, right. So, we can make use of this equation 45 in further developing our ideas. If we start writing out again the energy equation for the velocity field as it is written there, what we could do is we find then this is what we get if I take that energy the momentum equation and take a dot product with the velocity field, then we get the time rate of change of kinetic energy here, that is given in terms of this. This comes from the viscous dissipation term, and this comes from the body force term, right. And since now we have established this quantity itself is equal to entropy. So, you can very clearly see what is the role of entropy. Entropy actually tells you how the energy is drained out because of this viscous diffusion term, right. So, entropy is a very, very powerful tool. Now, what happens is we could also see that entropy could be written in terms of its entropy squared is nothing but grad u squared. So, what is grad u? Grad u will be, if I am talking about this, so this goes as okay. So, if I write u in terms of u hat e to the power I k x d k, then what happens to grad u? So, this is, I could write it as k vector dot say r vector. Okay. So, then what happens is I could get this would be equal to nothing but proportional to I k vector u hat, which is a function of course, this k vector times e to the power I k dot r d k. So, now if I square it up, I can see that this is going to be like k square and this is this. So, this goes like this, right. So, this goes like this. However, this is what from the Parseval's equality, this also represents E of k, right. If this is the specific kinetic energy in the k space, that is also the kinetic energy in the so this has a role as we have written down here, E of k, right. So, basically the vorticity is something like this. Now, consider a packet. Let us now consider a packet of energy which is initially concentrated at a low k value. Okay. And suppose the body force is not acting upon at the low k, and you are also neglecting the effect of viscosity at very high k, then what happens? If we are looking at inviscid flow, I know the energy is conserved, right. E k d k is conserved, that is what we have obtained. What happens to the vortex stretching work? That we have seen, that increases the entropy, right. That is what we have been talking about here, that if I well, we saw it that if because of stretching this will increase, entropy increases because of vortex stretching. So, if entropy increases, then what is happening? We have given an estimate of entropy as k square E k. So, what is happening is we have a very interesting situation, that this is conserved, E k d k is conserved, whereas k square E k d k is increasing. How can that happen? It can only happen if you transfer the energy from low k to higher k, because it is multiplied by k square. So, if this contribution has to increase, then I have some low k contribution in E, transfer it to high k. This is the mechanism of energy cascade due to vortex stretching. So, that is what we have been talking about. We were talking about this idea for a long time, what E k does with k, that if I talk about vortex stretching, this will essentially do that. That if I pump in energy here at low k, because the vortex stretching term, that energy has to shift to this. So, this is what we would be calling as the cascading effect. The energy cascades, that is what we are talking about. So, that is why I show it with a very bold remark here, that this is the mechanism of energy cascade, and this is a nonlinear effect, right. In fact, this idea has been so much entrenched into the thinking of turbulence community that people do not like to acknowledge that there can be any other mechanism of energy transfer. So, whenever you look at source material, people only say, oh, turbulence has to be 3 dimensional, it cannot be 2D because there is no stretching. So, how is energy spectrum be explained? But we have lots of counter examples. We have seen like Kelvin-Helmholtz instability is one, where we saw what was happening. Bigger eddies were breaking down into smaller eddies. So, that means what? And you know Kelvin-Helmholtz instability is more dominant in 2D flows compared to 3D flows. So, here are counter examples, people conveniently forget. Then we have also seen bypass transition effects. What did we see? That if a single vortex is just simply moving at a constant speed, there is no trace of any unsteadiness. But what happens down below in the boundary layer? We get vortices erupting all over the no slip boundary, and that is a very high wide band phenomena. So, there are some things, but please do understand that for 3D flows at least vortex stretching helps you explain how energy is transported from low k to high k. Well, we have all of course noted that if we are looking at real flow, entropy increases. Okay. Now, if I look at the role of viscous terms in k space, the viscous term is like this, right. This is the second derivative of u. So, that will be minus nu k square u of k. So, if I am talking about u as a velocity scale, then I can say the viscous effects are negligible compared to the nonlinear term. So, this is your viscous term, right, no nu k square, and this is your convection term like del u del x term. So, del u del x will be nothing but I k times u. So, that is this. So, if this is the case, if viscous term is less, then what does it correspond to? That this k L is much smaller compared to R e. So, what does it mean? That those events are, because these are the places where viscous effects are going to be negligible for those cases. And which are those cases? They are small cases, right. That is what we are saying, because R e is large, and to have this condition validated, we must have the corresponding k, non-dimensional k, much smaller than R e. So, if I am talking about it, so this is the region, where the viscous effects are negligible compared to the convection terms, nonlinearity. On the other hand, if you look at nu k square far greater than this, that will be what? Those corresponding k's will be much larger compared to R e. So, if you prescribe a flow with a given R e, so it basically gives you a kind of a line of demarcation. On one side, to the left of it, viscous terms are unimportant, to the right of it, viscous terms are important. So, you can see that when we are talking about it, so if I draw a line non-dimensional k along like this, so this is the boundary that is determined by, let us say, R e. So, on this side viscous effects are unimportant, on this side viscous effects are important, right. So, that is one way of interpreting this slide. So, that is what I said, that Reynolds number roughly demarcates the border in k space whose evolution is dominated either by viscosity or nonlinearity. So, we are talking about a truly time dependent flow, right. Turbulent flows are indeed time dependent. So, this is not something it is frozen, because what we are talking about, this border itself will keep moving depending on whether the nonlinearity is important or the viscous term is important, and both these terms keep changing with time. So, if that is so, this boundary line that we are talking about, which is of the order of Re, but will keep moving about, right. This is something we should remember. Okay, if at all we arrive at a statistical steady state, flow is unsteady, but we still can get a statistical steady state, then what happens? This is the picture that we drew, that we are providing energy at large physical scale or small k. That could be due to body force, that could be due to many things. If I put in a sort of a cylinder in a flow, that the size of the cylinder determines what is the largest size of eddy that will be formed. So, there the disturbance energy gets created at small k. Then we have seen nonlinearity takes over and it creates this cascade and it goes over there. It comes there and it cannot go on indefinitely, it goes and stops somewhere where actually the viscous losses are transported into mechanical energy, is converted into thermal energy, right. So, heat is getting created. So, that is what we mean by kinetic energy being dissipated by viscous action at high weight number. So, if I am now talking about this scenario for a time dependent flow, then what can happen? I am putting in something here, I am taking it out here. So, a steady state has reached. That means what? Whatever is put in there, the same amount goes out there, right. That is your definition of an equilibrium steady state. That is what Kolmogorov started looking at, and he said that at the steady state the energy input rate on average is the same as the energy dissipation rate. Now, let us look at the average energy dissipation that we have seen, nu times gradient u square, right. So, what happens? What happens is we can find out it is a time scale. So, what is it going to be? Nu is what? Nu has a dimension of right L square by T. Now, what about grad u? What is its dimension? Right. So, what is the dimension of epsilon then? It will go like L square T to the power minus 3, isn't it? That is what we are seeing, this into this squared. So, that is what we say, the dimension of dissipation is L square T to the power minus 3. Now, if I have reached a steady state, I am pumping in energy here, I am pumping in energy there. So, what happens to some range in the middle? It does not matter what you are putting in on the left and what you are taking it out on the right. That is precisely what we are saying, that we can have some such range where the energy density spectrum E k is independent of what you are putting in and what you are taking out, right. So, what will happen? If I am looking at there, this intermediate scale which I called as the inertial subrange, the structure of E k is determined solely by the nonlinear energy transfer mechanism, how this cascade is going, how far it will go, whether it comes and stops here or whether it goes there. So, it depends on what? Where exactly this energy is taken out. So, the dissipation is important. It will also of course be function of k, because that is what we are looking at. We are looking in the k space. So, what happens to the energy at this k is different than this. So, there is a direct dependence on k. So, basically in this inertial subrange, which is neither on to the left or not to the right, in the middle we are talking about the middle ground, which we call as the inertial subrange, where this epsilon would be a function of epsilon and K only, right. Why do not we talk about the energy supplied? Because that is itself equal to epsilon, right, because we are talking about the steady state. So, they are same. So, that is why I did not put 3 terms, 2 terms are adequate, because energy input is equal to energy output, outgo. So, that is why we can write this E as this. Now, what about dimension of E? How do we go about doing that? See, dimension of E, if you recall, it is something like this. The energy is something like this, right. And what was it that we saw? That was like E k d k. Fine, you agree with me? So, what about this then? So, this is the right hand side dimensionally is dimension of energy, and what about dimension of k? L. Okay. On this side, what do you have? L t to the power minus 1. So, L square by t square. So, E, dimension of E then is going to be L cube t to the power minus 2. That is what we have written. Dimension of E k is L cube t to the power minus 2. Now, you have the dimension of E. We said that E is a function of epsilon, E is a function of k, right. So, we have already seen what is the dimension of epsilon, right. The dimension of epsilon is and this we have seen the dimension as we have given is L cube t to the power minus 2. Now, k's dimension of course we know is 1 over L. Now, all you will have to do is do a little bit of dimensional analysis. Those that will tell you this is it, that this in the inertial subrange energy spectrum is given by this. This is a fantastic result, very simple in approach, but very far reaching in consequence. What we find that in the inertial subrange the energy varies as k to the power minus 5/3. So, this is the result by which the whole community swears that we have an inertial subrange in turbulent flow, which does not depend on how you put in the energy, how you take out the energy. The energy spectrum has a universal feature. That feature is given by its dependence on k by this exponent of minus 5/3. Okay. So, this is the story that we are talking about, but please do understand that this is the story for a 3D flow, because here we are talking about nonlinearity, the vortex stretching coming into picture. So, this will not be the case for 2-dimensional flow. Okay. Time permitting, we will see that for 2-dimensional flow that E of 2D that goes as k to the power minus 3, and here what we are seeing is E of 3D goes as k to the power minus 5/3. So, do understand that if you have a way of measuring the energy spectrum and you look at different k range and you see what kind of slope it has. If it has a slope of minus 5/3, you can see 3 dimensionality is important, and if you see the slope has minus 3, then 2-dimensional aspect of the flow is important. An interesting part is what you know. You look at our weather system, you will find out first you get this k to the power minus 3. So, weather prediction actually has survived by treating this flow problem layer by layer. So, in that each layer it is a kind of a 2D problem. 3 dimensionality is stacked one over the other. So, it is like your onion peel, you can peel out one layer over the other, but mostly the dynamics is dominated by this 2 dimensional motion. Anyway, that is what is also the reason you know why shallow water wave equation plays such a central role in weather prediction, because that defines the 2 dimensional motion in that plane. Okay, so what we have now, we have learned something very interesting about turbulence, that we have an inertial subrange in all turbulent flows, and that is where we get k to the power minus 5/3. However, it gets cut off at a very high k. So, there is a cutoff scale. What it will be determined upon by the rate at which the energy is supplied, that is also the rate at which it is dissipated, and also it should depend on the property of the flow, and what better quantity of that is than your kinematic viscosity itself. So, this cutoff scale must depend on epsilon and okay. So, now I think we have a fairly a decent idea what happens in a turbulent flow, which we get by very little investment. We have mostly depended upon dimensional analysis, and we have said something which are very true, that if we have a statistical equilibrium steady state, then the energy that comes out here cannot reside there because of the importance of the role of the nonlinearity versus the viscous term. In this small k range, nonlinearity is important, that pushes the energy to higher k, and it keeps on going, and somewhere down the line it must dissipate itself into thermal energy, and that is what we are talking about. That there is something, if I am plotting this k, then there is some k cutoff, I will call it as kc, right. This cutoff scale will depend upon the rate at which the energy is supplied or taken out, and also the material property, the fluid property. And what is the split property? That we have already seen, that is the Reynolds number of the problem, right. Reynolds number directly incorporates the kinematic viscosity. So, what happens is this cutoff scale can then change. What happens if the value of Reynolds number is large, we can actually go to much higher k. The smaller the Reynolds number, that means larger the value of nu, it has to end earlier, because that is where viscous dissipation takes over. Okay. So, this is something that we must keep in mind, that this cutoff scale will become smaller if we either increase epsilon or decrease nu. Increase epsilon means what? I am putting in more energy. So, I am allowing it to go for larger range of k. Decreasing nu means what? I am talking about higher and higher Reynolds number problem. So, that allows me to sustain larger rates of strains. So, that also allows me to go there. So, that is precisely what we have stated out there. Now, what you do is we have epsilon, we have nu, we have seen the dimension, we have the epsilon here, nu dimension is given by L square by T. So, what I could do is I could use it to define a length scale or which I call as lambda k. That I am going to define purely from epsilon and nu, whose dimensions are given, right. And if we look at this, this is the only possible combination that you can think of, right. So, basically that is what you are going to see, that this lambda k is C k times nu cube by this thing. So, that is rather interesting. This is what exactly we are saying, that how far we go, this k c. K c is what? If I look at this k c is the wave number, right. So, that will be 2 pi by lambda k, the corresponding wavelength. That is what we are saying. So, that lambda k, the length scale, in terms of nu and epsilon would be written like this. Okay. So, what we are talking about, we are trying to estimate how far we can go, and that is what Kolmogorov said, that at that scale, at the cutoff range, everything would be determined by epsilon and nu, and then the corresponding length scale is this. You can obtain a corresponding velocity scale exclusively in terms of nu and epsilon. You can construct a time scale exclusively again in terms of nu and epsilon. So, we get these 3 scales. That more or less defines everything, is not it, the way we have been non-dimensionalizing Navier-Stokes equation. What we needed there, a velocity scale, a time scale and a length scale. So, we have all 3 of them. What is interesting is sometimes, of course, we have what we have done. We have converted the velocity scale and length scale into a time scale, right. We can do that, but here we are talking about, let us say these 3 things are independent. If it is indeed so, I could construct also a Reynolds number. This Reynolds number is not the flow Reynolds number. This Reynolds number is the one where I have taken a velocity scale which I am calling as v, the length scale as a lambda k, and this is nu. And the velocity scale we have seen in the previous slide. We have seen what is the lambda k scale substituted there, and then we get this. So, lambda k was in terms of a undetermined constant C k, which is of order 1, right, which has to be order 1, the way we have reasoned out. So, what we are finding, that the Reynolds number is order 1. What does it mean? We roughly speaking, we always estimate Reynolds number as a kind of a relative weightage between the convection term vis-a-vis the viscous term. So, if Reynolds number is 1, so this is the scale at which the viscous terms are as important as the nonlinear term, right. So, these scales where the viscous effects are as dominant as this is what are called as the Kolmogorov microscales. This is where you can go at the most, given a flow field, given the flow property, you can go up to maximum the microscales, Kolmogorov microscales. And one of the properties of turbulent flows that we discussed, remember, we said that this microscale is, compared to molecular dimension, it is significantly larger. So, Kolmogorov microscales are still much larger compared to your molecular dimensions, and that is why we can actually view turbulent flow in terms of Navier-Stokes equation itself, because the smallest length scales, those are excited, they are significantly larger than the mean free path, and that is one of the reasons that we do use the Navier-Stokes equation as the governing equation for. Okay. So, now we have a very decent view of the energy spectrum, that we can obtain this energy spectrum by equating rate of energy supply to rate of energy dissipation, and this was a kind of a equilibrium condition proposed by Kolmogorov, and this is goes by that name, universal equilibrium theory of Kolmogorov. It is not necessarily true that as simply as we have done in terms of dimensional analysis, Kolmogorov did it with statistical physics. So, that is a much beyond the scope of this course. I will not talk about it, but we have the gist of it in front of us and we can see. based on the scaling theory, we can sketch the energy spectrum as a function of wave number for 3D flows. In turbulent flows, the wave numbers are excited over a broad band, and this is what you would like to see. See what happens when we talk about laminar flow. We then get to see something like this. We may get one peak here, another peak there, another peak there. That is what you see, right. You have very, very discrete peaks, not wideband spectrum like what we are seeing here. It is not a broadband phenomenon. So, basically this broad band is also quite important, because what happens is we are going to plot it like this in a log scale. That is the way we are going to plot the energy spectrum in log plot. What is happening is energy also spans over many decades, and so is the wave number. Think of nothing better than say our weather system. The largest length scale that you can think of is the periphery, if you circumnavigate the whole world. So, it is what 2 pi into 6,000 or something. So, it does work out about 24,000 kilometers, something of that kind. And at the small scale, you can see even when a leaf is swaying in the wind, that is the smallest scale that you can think of. So, you can think of this huge range of scales that you can think of, coming from a few centimeters or even millimeters all the way up to thousands of kilometers. That is why we plot it in the log scale, and this is how it is. If we are looking at a 3-dimensional flow, this is how it should be. This is your inertial subrange, where the dependence is upon like this k to the power minus 5/3, and this is where you have pumped in all your energy. This is how turbulence was created. If I put in a body, that is where I put in the energy. Energy migrated along this and got dissipated in Kolmogorov microscale. So, that is what you see, that this cross belongs to log 2 pi by lambda k. This is your log of 2 pi by L, characteristic dimension of the problem, right. Talk about flow past a chimney, it is the diameter of the chimney. Flow past a aircraft wing, it is the chord of the wing. So, it is that kind of thing that we talk about, the outer scale or the characteristic dimension, larger length scale, and the smallest length scale is of course determined by Kolmogorov scale. Now, what we could do is we could talk about little bit about the feature of this energy spectrum. The inertial subrange has universality only when you are talking about really high Reynolds number, because flow has to suffer those instabilities to go from laminar to turbulent flow. And you do need to have a significant stretch where this is independent of what is happening on this side and what is happening on that side. What happens if I look at a lower Reynolds number turbulent flow? It could be something like this. So, this dynamic range probably comes down by let us say factor of 100 or factor of 1000. So, low Reynolds number flows, you may not actually even get this part, that k to the power minus 5/3 part, that is what we are saying. Whereas, the structure at the low wave number is non-universal. The details depends on how you set up the flow, right. That is what we are talking about. However, if I am looking at the viscous cutoff that actually cuts off the energy, that is determined by Kolmogorov scale. So, at least 3 things we have, and 2 are kind of determined if Reynolds numbers are high. One is of course the microscale, and the second is inertial subrange. What happens in the low k range? We have no idea, because it is flow dependent. We are going to have different flows, will have different. Now, this is one thing that I wanted to talk to you about. It is about the necessity to view the dissipation spectrum. This also you look at in the k space, and this is quite straightforward. Dissipation is, if you recall, nu times the grad u squared. So, that was simply nothing but nu times k square E k. Okay. If you look at this, well, you can very clearly see that is what we have written here, that d is proportional to nu times grad u square. Grad u itself is k u hat of k. So, the d is then proportional to nu k square. This itself is like your E of k u hat square. So, that is what we are saying, that d k goes like this. So, what happens is, if I have the energy spectrum sketch, from there I can also work out the dissipation spectrum, right. That is the relation given there, and this is what we can also see, that we can plot the energy dissipation, which is given by nu times the fluctuating strain rate. So, that is your d k E k, that is the definition of d k, right. So, basically then I can see what d k is. D k is nu times k square E k, that is what we are going to plot. This is how it is going to look like. It is a kind of a sketch. So, do not take too figuratively. Now, how do you get? What did we write there? D k goes as nu k square E k. Now, what is E k? E k we have just now seen goes like this in the inertial range. So, in the inertial sub range, what do we get? D k goes as nu k square and E k is k to the power minus 5/3, right, and of course, those epsilon term is there. So, that is not the issue, but you can see d k then goes as k to the power plus 1/3, is not it. So, that is what you are seeing here. In the inertial sub range, it goes as k to the power 1/3, and at the low k range, that we have already seen. We have said that that is the place where viscosity is not important. So, d of k is negligible. So, it kind of starts off from where the flow begins. It picks it up, but in the inertial sub range it goes up as k to the power 1/3, and then again it is all lost due to dissipation. So, that is at the Kolmogorov scale. So, what you find is this. So, this is a very instructive picture, which many people do not keep track of, is if I plot this as E of k. So, if this is my E of k, which goes like this, my d of k goes like this. So, you see, when you are let us say trying to compute, this is important in computation, that people tend to think that I will do LES and all I need to do is worry about E of k. I will short circuit this E of k somewhere and I say, oh, I am doing it. But people do not talk about what they have to do correspondingly to the d of k. But the d of k has this structure, and d of k is more important maybe in the scale which is beyond this. So, that is at your subgrid scale. So, think of the subgrid scale modeling, it is not a trivial exercise. You will have to model it appropriately so that it mimics that d of k property, right. So, this is something one must do when you generate a subgrid scale model for LES. Make sure that at least in the inertial range it should have this kind of attribute. If it is not, then you have a very poor model. Okay. So, this is your dissipation spectrum, and we can do all kinds of things. We can play around with all these numbers that we have seen, and epsilon we can use this previous equation that we can now talk in terms of the range where it is becoming important. So, d of k we have obtained. So, I substitute d of k expression here and integrate over all possible k, and k now goes from 0 to 2 pi by lambda k, that is the Kolmogorov length scale, and I get this. Already we have seen that lambda of k goes like this. This is your Kolmogorov length scale that we have obtained from dimensional argument. So, we can plug this last expression in the previous one, and what we get is that this c of k, that there are lots of floating constants that we are talking about. So, this c of k, lowercase c of k, is related to capital C of k, is like this. So, what it means is there are not too many c of k's that you will have to be looking around for, because there is a unique relation between the two. If you obtain one of them, the other one gets frozen. That is what we are saying. This floating parameter is determined by some experiment or by some statistical analysis tools, etc. Okay. Now, what we have talked about, that Kolmogorov spectrum allows us to define a Reynolds number, because it provides a velocity scale by this following parameters, epsilon, nu, and the length scale L. The velocity scale is obtained from the total kinetic energy per unit mass. That is quite easily understood. Okay. So, that is given according to this, and then we find that this is a specific kinetic energy that is by definition given by this E of k dk, and this E of k I have already gotten that expression, I substitute it there. So, I find u goes like this. So, if I look at Reynolds number, that is u L by nu, it goes like this. Okay. So, we have obtained the value of epsilon in terms of Re here, and I can now plug it in back into the expression for lambda k, that goes as this. I think I will stop at this point. Tomorrow I will take first few minutes to expound upon this, and then we will have our general discussion session. Okay.